Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the last lecture. In the last lecture, we started the topic, namely, let me write the topic application of statistical method to gases. So today we will continue this topic by write continued. So remember, in the last lecture, we said that when we compare the application of statistical method to gases, when we compare this with the case of an assembly of distinguishable localized particles, we have to incorporate two ideas. One idea concerns the one particle states. We said that a gas particle is confined to a large macroscopic box of volume V, whereas a localized particle is confined essentially to an atomic cell of volume V by N. As a result, the energy levels of a gas particle are extremely close together. And we said astronomical numbers of them are being occupied at any reasonable temperature. So this is one difference between gas and a localized assembly of distinguishable particles. In the localized case, energy levels are comparatively far apart, and the occupation of only a few need to be considered. The second idea we discussed in the last lecture is how to deal with the indistinguishability of gas particles. We know the gas particles are indistinguishable, and we have to consider that because that is vital to the counting of microstates. Then we said in the last lecture that these two ideas are both essentially quantum mechanical. Then we discuss how the state of a gas particle can be discussed according to quantum mechanics in terms of a wave function. And we considered a gas particle in a box of volume V, which we considered for convenience of calculation in the form of a cube with side A, and we wrote the stationary states for the particle of gas. We wrote this equation. Let me write that. Psi sine of, we are ignoring the normalization constant, sine of n1 pi x by a, sine of n2 pi y by a, and sine of n3 pi z by a. This was our equation first. Sine of n1 pi x by a, sine of n2 pi y by a times sine n3 pi z by a, where the positive integers n1, n2, n3 simply give the number of half waves fitting into the cubical box of side A in the X, Y, and Z directions respectively. Then we talked about the density of states. First, we wrote this in terms of the wave vector. Let me write that equation. Let me change the color here. So we wrote this psi in terms of the wave vector k. We wrote it this way, psi as sine kxx times sine kyy times sine kzz. This was our second equation. Remember, kx, ky, and kz are the components of the wave vector k. Then we talked about the density of status function g. We wrote this equation. G of kx, ky, kz times delta kx, delta ky, delta kz. This was equal to a by pi whole cube times delta kx, delta ky, delta kz. This was our equation third. I will refresh your memory. In the last lecture, as I told you, this left hand side in this equation 3 is representing the number of states in the group whose k vector lies with its x component between kx and kx plus delta x, with y component between ky and ky plus delta ky, and z component between kz and kz plus delta kz. A is the side of the cube. So A cube is actually the volume in which we are considering our gas particle to be confined. Then we talked about another density of states function. We wrote another equation. Let me use another color for that. We wrote the equation for g of k delta k. This was equal to v over 2 pi whole cube times 4 pi k square delta k. This was our fourth equation. Gk delta k, v by 2 pi whole cube times 4 pi k square delta k. Where this left hand side in this equation 4 represents the number of k states with values of scalar k between k and k plus delta k. V is the volume, and you know 4 pi k square delta k in this expression arises as the volume of a spherical shell of radius k and thickness delta k, and 1 by 8 factor in this equation 4 comes since we only require the 1 by 8 of the shell for which kx, ky, and kz are all positive, that is the positive octant. Now this equation 4 is the most important result with regard to the statistical method when we apply this method to gases. This equation 4 is a three-dimensional result based on the volume of a spherical shell of radius k. Entirely analogous results can be derived for particles constrained within one or two dimensional boxes. Let me write the results directly. In two dimensions, in two dimensions, that is, if a gas particle is confined in a sheet of area A, then density of states in K is given by G of K delta K is equal to A by 2 pi square times 2 pi K delta K. This is my equation 5. What is this? This is the density of states function. That's my left hand side is the number of states with K values between K and K plus delta K for a particle which is confined in a sheet of area A. So A, capital A here is the area of the sheet in which the particle is supposed to be confined. So this is the result, A by 2 pi square times 2 pi K delta K. So you need to check this at home. This is your home assignment. Check it. Similarly, in one dimension, how we write this expression in one dimension? That is, if our particle is confined in a length L, then G of K delta K is equal to L by 2 pi delta K. Let me name this equation 6. You have to check this also. Check it. What is L? L is the length in which the particle is confined. So this is 5 and this equation is 6. Right? L by 2 pi delta K. It's okay. Now, this is not the total story about the application of statistical method to uh, gases. When we apply, we need other ideas. Let us discuss those ideas. Think about these two questions. First question. The first question relates to what constitutes a quantum state for a particle, right? Remember, the K state of the particle, which is specified by the equations we discuss, these states we call K states, which are expressed by these equations, because these states are specified by the k values. We call them k states. The k state of the particle as given by these equations or considered in these equations which we wrote is actually a full specification only of the translational motion of the center of mass of the particle. So you need to understand, let me write it. The k state specifies only the, let me fix my pen, specifies only the translational motion of the center of mass of the particle, of the center of mass of the particle, that is the gas particle which we are taking into consideration. And the states are characterized by the psi which we discussed. So the psi which we wrote and the states which we specified by the k values, they specify or take into account only the translational motion of the center of mass of the gas particle. But usually there are other identifiable things one can say about the gas particle besides its center of mass motion. Firstly, one may need to consider the internal motion of the particle arising from vibration or rotation of a molecular particle. So when we take those vibrations or rotations of the gas particle into consideration, we have to take that into consideration mathematically. These equations are ignoring those internal degrees of freedom which we call, they take only the translational motion of center of mass of the particle into consideration. So one question is that we have to take, when we take into consideration the full state of the particle in question under consideration, we have to take those internal degrees of freedom into consideration or into account. Second thing, let me write the second question or second thing which you have to consider. Second question or thing which we have to address while talking of the state, full state of the particle. That is, even for a simple particle, one must specify the spin of the particle. One must specify the spin of the particle. So we have to address that issue. We have to take into account the spin of the particle or the polarization of the corresponding wave which represents the particle. That is essentially the same idea. For example, an electron with a particular spatial wave function and it is spin up is in a different quantum state from an electron with the same spatial wave function, but it is spin down, right? Similarly, for an electromagnetic wave, one needs to know not only its wave vector k, but also its polarization. Only then you can specify that wave. So these two things we have to take into consideration. One is the spin or the polarization of the corresponding electromagnetic wave, or I should say the corresponding wave, or and then second thing, we have to take into consideration the internal degrees of freedom. Now, how we deal with that, we redefine our states. Let me write. So what we do, we redefine g of k delta k. We define it to be the number of quantum states when we label them as the number of quantum states, then they are not merely k states, not merely k states. How we mathematically do that? So if they are the number of quantum states with the magnitude of k between k and k plus delta k, then we write this equation for them. G of k delta k equal to v by 2 pi q times 4 pi k square delta k. Let me use another color to modify this equation. We multiply by a factor g here. So let me write this as equation. This is my equation 7. So this is my equation 7. Let me check it. V by 2 pi cube 4 pi k square delta k g. While this new factor g is called the spin factor or polarization factor. So it is spin factor or polarization factor, right? And this spin factor is usually 1 or 2 or another small integer dependent on the type of substance under consideration. So when you talk of the density of states function, you have to be cautious which states you are talking about, whether they are k states or whether they are quantum states. Quantum states is a different thing. K states is a different thing. Quantum states are k states plus something, right? Another thing which is vital to the application of statistical method to gases is it's not only sufficient to count up the quantum states, we must also know their energies, which in earlier lectures or classes we have specified by epsilon j. Energy of the jth state. We have to specify the energy of these quantum states also, because we know all equilibrium thermal properties are governed only by energy. And we know the two constraints on an allowed distribution are those of energy and the number of particles in the system, right? So we have to find that energy. Now what we do, we write another density of states. Let me write another equation. That's called G of epsilon delta epsilon. What is this? Epsilon is the energy. So it is density of states in energy. So it is what? It is number of states with energies between epsilon and epsilon plus delta epsilon this and sorry. So G of epsilon delta epsilon is the number of states with energies between epsilon and epsilon plus delta epsilon. So G of E is the density of states function in energy. It is different from G of K. Now, how we get to this density of states in energy? We use the EK relation. See, this energy and K, that's the magnitude of the wave vector, are related. And their relation is called, let me call it EK relation. We call that dispersion relation. So that dispersion relation depends on the problem under consideration. So once we have before us the density of states in K, then we go to or switch to density of states and energy through the application of the EK relation or the dispersion relation. So what we do using that dispersion relation, we convert this from the dispersion relation, this K square and delta K, to bring this into the energy form. Then we get the expression for density of states in energy. So you need to consider this. Another thing which you need to consider is that's the idea of distribution in groups. Let me write this. These subtopics all come within our main topic, application of statistical method to gases. What is this idea? Distribution in groups. So idea is like this. As we now know that the number of relevant one particle states, Ej or epsilon j, in a gas is enormous, often very much greater than the number n of gas particles. So for convenience of calculation, what we do, we group these states. Let me draw a figure. When we group the energy states, we call this grouped distribution. Let me draw a figure to make this clear. Use another color. Suppose this is my true distribution of the states. So what do we do? We group some states like this. Let these states in this group, let the number be GI. So I group GI states into single state, which I call ith level. This ith level is containing GI states. Similarly, we group another group of states into another level, another group of states into another level, and another group of states into another level. So this is left side is my true distribution of the states. My right side, which I obtained by grouping the states, we call this grouped distribution. Now each level, ith level in this grouped distribution is containing actually GI states, and GI is large, right? Now you need to understand one difference, that is when we take this ith level containing GI states, it contains many states, it contains GI states, but we take their average energy as epsilon I. Average energy epsilon I. That means all the GI states in the ith level have the same average energy epsilon I, right? In true distribution, their correct individual values are different, but in group distribution, when we take GI states in the ith level, we take their average energy as epsilon I, right? Now, why we do this grouping? This is not necessary, but it is convenient for our calculation purposes, because we know the number of states GI is large, and also the number of particles Ni occupying these states is large. So we can use the mathematics of large numbers, that is Stirling's approximation, in discussing Ni and Gi, right? In order to work out the thermal equilibrium distribution, which is our next step. Only one thing we need to take into consideration is that in grouped distribution and true distribution, the number of states must remain the same. Otherwise, this grouping is arbitrary, right? This next thing what we do in this discussion, we group the states. So when we say GI states, we have actually grouped through some states into single state, which is ith level, And in the ith level, all GI states have the same average energy, epsilon I. The next thing which you need to consider, we define here another thing that's called the distribution function. We define the distribution function. That distribution function is written as, I will write Fi. Fi by definition is Ni by Gi. So I have Gi states. Those Gi states are containing Ni particles. So Fi is the ratio. What is then Fi? Fi is simply the average number of particles per state in the group, right? So it is, let me first encircle it. This Fi we call distribution function. It is simply the average, let me write my here, average number of particles per state in the group. It is understood. So it is average number of particles per state. This is called distribution function. It is also sometimes called the filling factor. The filling factor, right? I stop here. We will continue this topic in the next lecture. So before stopping, I will again refresh this topic to you. I told you when we apply statistical method to gases, it's a different story than that of the application of statistical method to distinguishable particles which were distinguishable by means of their locality. Then we talked about why it is different. First thing, gas particle is confined to a large macroscopic volume. So there the number of energy states is large. Then the gas particles are indistinguishable. Then we use the quantum mechanics to specify the state of the gas particle. Then we talked about the density of states function in K. Then I told you this is not the full story. When we consider these K states, those K states are only specifying the translation motion of the center of mass of the particle. It ignores the internal degrees of freedom. We have to take those internal degrees of freedom, if they exist in the problem, into consideration. Second thing, we have to specify the spin of the particle also mathematically. Then we talked about the quantum states. So if gk delta k is the number of quantum states in the given range, then we have to multiply by another factor g here, which is called spin factor or polarization factor. Then we go from density of states in K to density of states in energy using the concerned EK relation or dispersion relation. Then we talked about this grouping. We group the states because the number of states is very numerous. So, but you have to remember that in the ith level containing GI states, we are taking all have same energy epsilon I. It makes our calculations convenient and easy. Then we define the distribution function or filling factor as the average number of particles per state, which is Ni by GI, where Ni is the number of particles in GI states. So it's all for today. Go through all the lectures and don't forget to like, share, and subscribe my channel. Thank you. Assalamu alaikum.